Welcome to the concept of scheduling. Scheduling is the process of prescribing when each operation in a production process is to be executed. As you can see from the PPT here, according to Kimball and Kimball, scheduling is the determination of time that is required to perform each operation and also the time required to perform the entire series of operations as routed. In short or in brief, scheduling can be termed as a detail of when and where each operation in the manufacturing process is to be performed or executed. Establishment of an activity timetable which gives the time to start or finish each event or operation comprising any procedure or process is generally called as scheduling. If we talk about the objectives of scheduling, the fundamental objectives of scheduling is to arrange the manufacturing activities in such a way that the cost of production can be minimized and the goods produced by the organizations are delivered on due dates. In general, scheduling meets the following objectives. In order to meet the delivery dates, the sequence of the operations should always be properly planned. To have the minimum total time of production by having better resource allocation, for having maximum capacity utilization and reducing the labor cost by minimization of idleness of the machines and the manpower, and most importantly to avoid the unbalanced allocation of work among the various departments and workstations. These are some of the most important objectives of scheduling. Before we go into some examples of scheduling, we have to understand certain terms or important terms that are associated with the performance measurement of the scheduling. The first one that we will be talking about is called flow time. Flow time is the time a job spends in the service or manufacturing system. The due past or past due is the amount of time by which a job missed its actual due date. If we talk about flow time and job and past due, then job is the object receiving service or being manufactured. The next thing that we need to understand is called make span. The total amount of time required to complete a group of jobs is called make span. Minimizing make span supports the competitive priorities of cost, which can lower the inventory and time, that is the delivery speed. So make span in short is equals to time of completion of the last job minus starting time of the first job. The second thing that we need to understand is called the total inventory. Total inventory is the performance measure used to measure the effectiveness of the schedules for the manufacturing processes. The sum of scheduled receipts and the on-hand inventories are called the total inventory. Minimizing total inventory supports the competitive priority of the cost, which is the inventory holding costs. The third term that we need to understand is called utilization. The degree to which equipment, space, or the workforce is currently being used, measured as the ratio of the average output rate to the maximum capacity. Maximizing the utilization of a process supports the competitive priority of cost, which in this case is the slack capacity. In case of job shop sequencing, basically two different kind of methods are used. The FCFS full form is the first come first serve basis rule, which gives the most importance to the job arriving at the workstation first. The early due date or the EDD rule gives the job with the earliest due date based on the assigned due dates the highest priority. The next thing that we need to understand is called the critical ratio or the CR. Critical ratio is calculated by dividing the time remaining until a job's due date by the total shop time remaining for the job, which is defined as the setup, processing, move and expected waiting times of all the remaining operations, including the operations which is being scheduled. So the formula for critical ratio is equals to due date minus today's date divided by the total shop time remaining. The difference between the due date and today's date must be in the same time units as the total shop time remaining. A ratio less than 1 implies that the job is behind schedule, and a ratio greater than 1 implies that the job is ahead of schedule. The job with the lowest critical ratio is scheduled next. The next term that we need to understand is called the shortest processing time. The job requiring the shortest processing time at the workstation under this method is processed subsequently, or we can say a priority sequencing rule is the shortest processing time that specifies that the job requiring the shortest processing time is the next job to be processed. Last but one of the most important term that we need to understand before going into the sum is S by RO or slack per remaining operations. Slack is the difference between the time remaining until a job's due date and the total shop time remaining, including that of the operations being scheduled. A job's priority is determined by dividing the slack by the number of operations that remain, including the one being scheduled to arrive at the slack per remaining operations. So by formula we can say slack per remaining operations is equals to due date minus today's date minus total shop time remaining divided by number of operations remaining. The job with the lowest slack per operations remaining is scheduled next. Ties are broken in a variety of ways if two or more jobs have the same priority. The one method of breaking the tie is to arbitrarily choose one of the tied jobs for processing next. Here is one example from scheduling. The sum says from the following data we need to find out the schedule based on the earliest due date and the shortest process time rule. We need to calculate the average flow time, the average hours early and the average hours past due. What has been said in the following columns that there are 5 engines A, B, C, D and E whose hours since order arrived is 12, 10, 1, 3 and 0. The processing time of the engines respectively are 8, 6, 15, 3 and 12, and the due date are respectively 10, 12, 20, 18 and 22. So as we have said previously, we need to find out the schedule using the earliest due date and the shortest processing time rule. Now from the above example we can now come back solving the sum first based on the earliest due day rule. Earliest due day rule, if we talk about earliest due day rule, we can see that A has the earliest due day of 10, B has the earliest due day of 12, whereas D needs to move from the 4th place to the 3rd place as its due date is 18. C will come down as it is 20 and E will stay last as it is 22. Subsequently, we have managed the hours since order arrived at 12, 10, 3, 1 and 0. The second that we will be talking about is the work beginning time. Now as we talk about the work beginning time, A is the first job that needs to be done. So if that is the first job that needs to be done, that is 0, and the processing time is of 8. So A will have the finish time which will be at 8. Finish time is generally achieved by adding up the work beginning plus the processing time. So finish time of A is subsequently 8, and the flow time is basically hours since order arrived plus the finish time, generally is giving as the flow time. So in case of A, subsequently it will be 12 plus 8, it will be 20. Now coming back to the work B, work beginning time is 8 after the A has finished, the processing time is 6, so the finish time will subsequently be 14, and the flow time will be the hours since order arrived, that is 10, plus the finish time which will be at 24. Coming back to D, now B has finished the work, B's work has been finished at 14, so D will be starting off at 14. The processing time of D is 3, so the finish time of D is 17. Simultaneously the flow time of D will be 17 plus the hours since arrived is 3, so the total flow time will be 20. Subsequently, if we look at C and D, C begins at 17, the processing time is 15, so the finish time subsequently is 32. The flow time added with the hours since order arrived, it becomes 33, and subsequently for E it becomes 44. Now up to this, if we have done, let's talk about the scheduled pickup. Scheduled pickup is the earliest due date that we have talked about. So it has been absolutely arranged as it should have been. And most importantly, now coming back to the actual pickup. See, students, that scheduled pickup of the work A or engine A is 10. But that engine's work had been completed, if you look at the finish time, is at 8. So even if the work is being picked up at 10, the work has been completed at 8. So hours early becomes 2. Is it clear to everyone? If not, I am repeating once more again. The scheduled pickup for the engine A is 10, but the work has been finished at 8, which has been indicated at finish time. So even if the customer who has given the engine A picks it up at 8, picks it up at 10, the work has been finished at 8, so the hours early is 2. Subsequently, moving on to B, the scheduled pickup is at 12, but actually the work has finished at 14. So actually the work will be picked up at 14, which gives us hour past due 2. Moving on to D, the scheduled pickup time is 18, though the work has been finished at 17. So it gives me an early hour of 1, which is given by the actual pickup time of 18. The engine C, scheduled picking up is 20, but actually the work has been finished at 32. So actual pickup time will also be 32, which gives the hour past due at 12. Coming back to E, the scheduled picking up of E is 22, the finish time is 44, the actual pickup will also be 44 since the hours past due will be 32. So finding out the average flow time is very easy. All the flow time divided by the number of engines gives us 28.2 hours. Average hours early, 2 plus 1 divided by the number of engines gives us 0.6 hours, and average hours past due is 2 plus 12 plus 32, which gives us divided by 5, 7.2 hours. So this is how we schedule the job based on the EDD rule. Now the same sum can be scheduled in a different way under the shortest processing rule, which we will be talking about here. If we reorganize the works or the engines based on the shortest processing time, we can rearrange the work as D, B, A, E and C, whose processing time subsequently are 3, 6, 8, 12 and 15. If we rearrange the order since order arrived, we will find D's to be 3, B is to be 10, A is to be 12, E is to be 0 and C is to be 1. So now if D is the first, should I say, work that needs to be started, so the beginning work is 0, the processing time of D is 3, so the finishing time of D is 3, beginning work plus process time, which we have talked about in the last slide also. And the flow time will be the finish time plus the hours since order arrived, which will be coming at 6. For the second job, the beginning work since D has completed at 3 will be 3, the processing time is 6, so the finishing time will be 9, the flow time will be finishing time plus 10, which will be 19. Coming back to A, the B's work was completed at 9, so initially the A's work will start at 9, processing time will be 8, so finishing time will be 17. If we add back the hours since order arrived with the finishing time, the flow time becomes 29. So now if the A's work has been completed at 17, so E's work will start at 17, the processing time will be 12, the finishing time becomes then 29, and if we add it with the hours since order arrived, the flow time becomes 29. And simultaneously the flow time and the finish time of C becomes subsequently 45 and 44. If we complete it up to this point of time, the scheduled pickup is given as after the rearrangement 18, 12, 10, 22 and 20. Now coming back to actual pickup time. Now see, the flow time or the work has been finished for D at 3, but the scheduled pickup is at 18. So the actual pickup will be at 18, but the work has been completed early by 15 hours. Coming back to B, the finish time is 9, but the actual pickup is 12, same as the scheduled one. So the hours early will be 3. Now the work A's scheduled pickup is 10, but the finish time of the work is 17, so the actual pickup time becomes 17, which gives us the hours past due at 7. Now the scheduled pickup for E is 22, but the finish time of the work is 29, so the actual pickup time is also at 29, which gives us the hours past due at 7. And the C subsequently will have the hours past due at 24 by the similar kind of method that we have talked about earlier. So the average flow time, very similar to the EDD rules, we need to add back all the flow time divided by the number of engines, which gives us 25.6 hours average flow time. Average hours early is 15 plus 3, which gives us approximately 3.6 hours, and the average past due is at 7 plus 7 plus 24 divided by the number of engines, which is giving us around a value of 7.6 hours. So this is the kind of scheduling that is done based on the EDD and SPT rule method. Now to clear up the doubts whichever was there from the previous example, let's take another example using the EDD and the SPT rule. The similar kind of calculation needs to be done about the scheduling, the average flow time, the average hours early and the average hours past due. And the same kind of work has been literally given to us with the 5 engines. Subsequent times since order arrived now has been given as day. The processing time also has been subsequently given to us, and the due date also has been given to us. So like absolutely similar to the previous sum. We have to find out the correct kind of scheduling using the EDD and the SPT rule method. Now, if we go on calculating the previous example using the shortest processing time method, the work or the engines needs to be rearranged at the following kind of rearrangement, which is D, E, B, A and C, since their processing time has been subsequently rearranged from the shortest to the longest, which is D at 1, E at 3, B at 4, A at 5 and C at 10. And the days since order arrived is subsequently rearranged at D at 1, E at 15, B at 6, A at 4 and C at 8. Now if we start off the work, first work D is started off at a time period of 0. The processing time is of 1, so the finishing time is of 1. The flow time is the days since order arrived plus the finish time, which is at 2. Now subsequently E will start off at 1, the processing time is 3, the finish time will be 4, and since the days since the order has arrived is 15, so 4 plus finish time, which is at 4 plus 15, gives us the total flow time of 19. B will then subsequently start off at 4, the processing time is at 4, the finish time is of 8, the days since order arrived is at 6, so the flow time will be 6 plus 8, 14. Subsequently A will be starting off at 8, the processing time is of 5, so the finish time will be 13, days since order arrived is at 4, so the flow time will be 13 plus 4, 17. Subsequently C starts off at 13, the processing time is 10, the finish time is 23, days since order arrived is 8, so the flow time is subsequently 8 plus 23, 31. If we now go back to the due date which was originally given, the original due date given was for D was 20, E of 10, B at 15, A at 8 and C at 12. Now the actual picking up, coming back, D has finished the work at 1, but since its due date is 20, actual picking up day will be also 20, so the work has been completed early by 19 hours. E, the work has finished at 4, but the due date is at 10, so the picking up will also be at 10, which gives us the early hours at 6. Coming back to B, the finish time is at 8, the due date is at 15, so the actual picking up day will be 15, which gives us the early hours at 7. Now coming back to A, whose due date was at 8, but the work has been completed at 13. So the actual picking time will be of 13, which gives us the hours late by 5. And C, which has been completed at 23, whose due date is at 12, whose actual picking date will be that of the finish time, that is 23. So the hours late will be, should I say, 23 minus the due date 12, so that will be giving me the hours late at 11. And simultaneously the average flow time is coming at 16.6 days, the hours early is coming at 6.5 days, and hours past due is generally coming at 3.2 days. Now moving on to the EDD method. Under earliest due date method, the solution needs to be, and the engine or the work needs to be constructed at a new kind of should I say arrangement, which gives us A, E, C, B and D, as the due dates are simultaneously arranged from lowest to highest. A is at 8, E is at 10, C is at 12, B is at 15, D is at 20. And the days since order arrived has been subsequently rearranged at A is at 4, E is at 15, C is at 8, B is at 6 and D is at 1. The processing time, let's start off now. If A is the first work that needs to be started, then it's starting at 0. The processing time is at 5. The finish time is at 5. The starting time plus the processing time. And subsequently then the flow time becomes the finish time plus the days since order arrived, which is at 9. The second work E starts off at 5. The processing time is of 3. So the finish time is of 8 and the flow time is 15 plus 8, which is the days since order arrived plus the finish time, which gives at 23. The third job to be started is C, which is starting at 8. The processing time is of 10. So the subsequent finish time of C is 18. The flow time of C will be the finish time, which is 18 plus the days since order arrived is at 8. So the flow time becomes 26. Next, the next job that's starting at 18, that is B. The processing time is of 4. So the finishing time becomes 22. Subsequently, the flow time becomes 22 plus the days since order arrived 6 at 28. The fifth job that is starting at 22 is D. The processing time of the work is 1. So the finish time of the work is 23. The flow time of the work becomes 24. From this, now let's go back to the due date and the actual delivery. The due date of work A is at 8. So the actual delivery will be of 8, but the work has been completed at 5. So the days early for A is giving at 3. Simultaneously, for E, due date is of 10. So the actually delivery date is of 10, but the work has been finished at 8. So days early becomes 2. Due date for the work C is at 12, but the work has been finished at 18. So the actual delivery is at 18. So days late becomes 6. Coming back to engine B's work, the due date is at 15, but the work has been finished at 22. So the delivery will be actually be taken at 22, which gives us the days late to be 7. Coming back to the last work or the work D. D's actual due date is at 20, but the work has been completed at 23. So the actual delivery of D will be at 23, which gives us the days late to be 3. Subsequently, the average flow time will be all the flow time added up divided by the number of work that has been given to us, which gives us subsequently 22 days. Moving on to average days early divided by total days early divided by the number of work, which gives us 1 day, and the average days late, which gives us at 16, adding up all the days late divided by the number of engine, which gives us subsequently at 3.2 days. Apart from the EDD method and the SPT method, in case of single workstation, the scheduling can also be done by two following rules, that is slack per remaining operations and the critical ratio. If I make you remember the formulas for slack per remaining operation and critical ratio, which we have talked about in the previous slide, I'll come back to the formulas later on. Let's see the sum first. While calculating the solution, we will be discussing the formula as well. So here it has been given the current date to be 150. We need to assume that it has been given. The works are A, B, C, D and E. The processing time simultaneously for A, B, C, D, E are 10, 7, 15, 4 and 8. The due date simultaneously are 162, 158, 152, 170, 154. The remaining operations are 10, 9, 1, 8 and 5, and the shop time remaining are simultaneously 9, 6, 1, 18 and 8. So under slack per remaining operation method, the formula for slack per remaining operation is due date minus the today's date minus total shop time remaining divided by the number of operations that remains. So if according to the formula, I'll make you remember the formula once more. Slack per remaining operations is due date minus today's date minus total shop time remaining divided by the number of operations remaining. So based on the formula, if we go and calculate the slack per remaining operations method for A, we talk about the due date of A to be 162, the current date to be 150, the shop time remaining is 9 for A divided by the remaining operation of A, that is 10, which gives the value of A to be at 0.3. B's due date is 158, current date is 150, shop time remaining is 6 and the remaining operation for B is 9. So the B's value under slack per remaining operation is 0.22. C's value, D's value and E's value, if we subsequently calculate using the same kind of formula, comes at 1.25 and minus 0.80. So the order in which the work or the methods that needs to be completed, or if we say the scheduling under the slack per remaining operations, is the values of the work or slack per remaining operations should be contributed to from lowest to the highest. So under that method, if we talk about the first work that needs to be completed is E, the second work that needs to be completed at B, third work that needs to be completed is D, fourth work that needs to be completed is at A, and the fifth work or the last work that needs to be completed is of C. Now coming back to the critical ratio method. Critical ratio, again the formula is due date minus today's date divided by the total shop time remaining. So now if we talk about A's due date, that is 162, minus the current date which is at 150 and the shop time remain is of 9. So the value of A comes at 1.33. Next, the work that is there is B, whose due date is 154. The current date is 150, the shop time remaining is 6, so the value is at 1.33 again. And C, D and E, simultaneously using the same values, we can have the values at 2, 1.11 and 0.05. Like the slack per remaining operations method, under the critical ratio method also, the work which is having the least CR needs to be completed first. And if you remember, if we had a tie under any kind of method, we need to be completing that work depending or picking up the work arbitrarily. So now if we go on completing the scheduling here, the first work that needs to be completed is E, the second work that needs to be completed is D. There is a tie between B and A, so arbitrarily if I choose A, you can arbitrarily choose B also. So if I arbitrarily choose either of one, so B is the third job needs to be completed, subsequently A becomes the fourth job that needs to be completed, and the last job that needs to be completed under critical ratio method is C. So these are the scheduling done by the slack per ratio operation remaining operations method and under critical ratio method. If any doubt was there from the previous sum, let's consider another example that we will be taking into consideration doing the schedule based on the critical ratio and the slack per remaining operations method. So here there is this is a bit different from the, should I say, the previous sum. Here it has not been mentioned the today's date. right? So if today's date has not been mentioned, so let's see how we can be doing that. So let's start off with the sum itself. It has been said that from the following data we need to find out the scheduling using the critical ratio and the slack per remaining operations method, where the jobs are 1, 2, 3 and 4. The processing time simultaneously are 2.3, 10.5, 6.2, 15.6. The time remaining until the due date are 15, 10, 20 and 8, and the number of operations remaining are 10, 2, 12 and 5, and the shop time remaining are practically 6.1, 7.8, 14.5 and 10.2. Now if we talk about the critical ratio method first, so if we go into the critical ratio method, we can easily now go back and talk about the formula for critical ratio. Since today's date has not been given, ideally the formula would have been due date minus today's date divided by total shop time remaining. So since today's date has not been mentioned to us, so we can say the formula to be due date divided by the total shop time remaining. So for job 1 we can say the due date is 15 and the shop time remaining is 6.1. so the number 1 jobs critical ratio comes at 2.46. Simultaneously for job 2 it is 10 divided by 7.8, that is the due date, divided by the shop time remaining, that is 1.28. The third one is 20 divided by 14.5, which is 1.38, and the fourth jobs due date is 8 and the shop time remaining is 10.2, so that is 0.78. so if we now follow the same kind of concept to rank or to schedule the jobs from lowest to highest, the first job that needs to be completed is 4, the second job that needs to be completed is 2, the third job that needs to be completed is 3, and the fourth job that needs to be completed, or the last job that needs to be completed, is 1. So coming back, as we were talking about that today's date has not been mentioned here. So simultaneously the formula for slack per remaining operations will move from due date minus today's date minus total shop time remaining to due date minus total shop time remaining divided by the number of operations remaining. So if we talk about this now, so the first jobs should I say slack per remaining operations is 15 minus shop time remaining is 6.1. If we deduct that and then divide it by the number of operations remain, that is 10, so the slack per remaining operations for job 1 comes at 0.89. Simultaneously for job 2, 10 minus 7.8 divided by the number of operations remaining, that is 2, so we get the slack per remaining operations at 1.1. For third and fourth, simultaneously the slack per remaining operations can be calculated at 0.46 and minus 0.44. Now if we try to schedule it based on the lowest to highest slack per remaining operations, the first work that needs to be completed is 4, simultaneously followed by 1 and 2. So the ideal scheduling of the job will be 4, 3, 1 and 2 under the slack per remaining operations method. Now up to this point of time we were discussing how to schedule job for one single station. If we have suppose a flow shop, should I say for 2 station, now what to do? Now we have to introduce a certain kind of rule called Johnson's rule. We'll come back to it. Let's talk about what do we mean by a 2 station flow shop or something like that. Say if we assume that a flow shop which has several jobs ready for processing at 2 workstations, and the routing of the jobs are absolutely identical to its nature. So determining a production sequence for a group of jobs to minimize the makespan has generally two advantages. That number one is that the group of jobs can be completed in the minimum possible of time, and the utilization of the two station flow is maximized. Utilizing the first workstation continuously until it processes the last job minimizes the idle time on the second workstation also. So to ensure that we have a certain kind of procedure that minimizes the makespan while scheduling a group of jobs on two workstation, which is called the Johnson's rule. S.M. Johnson is the person who had prescribed that, showed us that the sequence of job at two workstations should be identical, and that the priority assigned to a job should therefore be the same at both. The procedure of the Johnson's rule is based on the assumption of a known set of jobs, each with a known processing time and available to begin processing on the first workstation. The procedure of the Johnson's rule is the following. The step 1 is scanning the processing time at each workstation and finding the shortest processing time among the job which has not yet been scheduled. If two or more jobs have been tied, we need to choose any job arbitrarily. This is the first step. The second step is, if the shortest processing time is at workstation 1, schedule the corresponding job as early as possible. But if the shortest processing time is on workstation 2, schedule the corresponding job as late as possible. Understand this part very carefully enough. If the shortest processing time is at workstation 1, we need to schedule that work as early as possible. But if the shortest processing time is on workstation 2, we need to schedule that job as late as possible. And the step 3 is to eliminate the last job scheduled from further consideration. We will not in further consider the last job which we have already scheduled, and then we need to repeat step 1 and step 2 until all the jobs have been scheduled. Now moving on to one example that we need to calculate from the Johnson's rule is given at from the following data, schedule the jobs based on the Johnson's rule and also draw the Gantt chart, GNATT. Gantt chart is practically one kind of flow chart which shows us the ideal kind of scheduling based on the Johnson's rule. So the work that has been mentioned here are M1, M2, M3, M4 and M5. Under workstation 1, M1 has a time period of 12, but under workstation 2, M1 has a time period of 22. Under workstation 1, M2 has a time period of 4. Under workstation 2, M2 has a time period of 5. M3 under workstation has a time period of 5. Under workstation 2, it has the time period of 3. Under workstation 1, M4 has a time period of 15. Under workstation 2, M4 has a time period of 16. Under workstation 1, M5 has a time period of 10. Under workstation 2, M5 has a time period of 8. Now let's go back and try to schedule it based on the Johnson's rule. What was Johnson's rule? If the minimum or the shortest processing time comes at workstation 1, what we need to do? We need to schedule it as early as possible. And if the shortest processing time of any job is coming minimum at workstation 2, we need to delay it as long as possible. So we can see here job M3, workstation 2's time is the least one among all the time. So the job M3, according to Johnson's rule, needs to be delayed as long as possible. So out of the 5 job under step 1, I have put M3 according to Johnson's rule at the 5th position. So furthermore, I will not take M3 into consideration. That also according to the Johnson's rule. Now if we come back, now if M3 has been eliminated, now the work which has the shortest processing time is that of M2, which is at workstation 1. So according to Johnson's rule, I will schedule it as early as possible. So I will be placing M2 under step 2 at number 1 position and then eliminate M2 from further consideration. Now when we have eliminated M3 and M2, the next job which has the shortest processing time is again at workstation 2 M5. So again I'll delay it as long as possible. So what I will do, I have already placed M3 at the last position, so just before that position I'll place M5 at step 3 and then eliminate M5 for further consideration. Now if we move on to step 4, if I consider now M1 has under workstation 1 has the minimum time processing time or the shortest processing time. So I'll place M1. I have already placed M2 at the first job. So as early as possible, I can place it at the second position. So I have placed M1 and then should I say eliminated M1 from the further consideration under in step 4. And the work remaining is M4 which I have placed in between. So the entire scheduling based on the Johnson's rule is M2, M1, M4, M5 and M3 for both the workstations. Now if we consider as Johnson's rule has been telling us that if we follow this particular scheduling under workstation 1, what we can do, we can generally put the idle time or any kind of slack that is there in the operation at the end of the period. So under workstation 1, if we follow that particular scheduling, M2 to M1 to M4 to M5 to M3 and then put the idle time, so what we can have the work schedule M2 and the values that has been written in between or below here are just the values or the processing time of workstation 1 for those kind of works. Coming back now, how to draw the Gantt chart in workstation 2 once the idle time has been put at the back end. So now see, the schedule will be same for workstation 2, M2, M1, M4, M5 and M3. This will be the actual schedule. Now see, if in workstation 1 M2 is working, I cannot work M2 simultaneously in workstation 2. So the 4 processing time that will be idle at the beginning and then I will work M2 in workstation 2. The processing time for M2 at workstation 2 is 5 and first idle time is 4. Next, again M1 is working for workstation 1 for 12 days. So the ending time from M2 and M1 is 16 days, 4 plus 12, and M2 has worked and completed, the work of M2 has been completed in workstation 2 in 9 days. So the remaining time will be the idle time here, that is 16 minus 9, that is 7. Now M1 will work simultaneously in workstation 2 for 22 days and then you will not find the idle time furthermore down the line. So if we now put all the values of M1, M4, M5 and M3, we find out the total time span, and that total time span is of 65. That is the minimum time span that is required to schedule the entire operations based on the workstation 1 and workstation 2. This is how we schedule any simultaneous jobs workstation or 2 workstation based on the Johnson's rule, and this is how we draw the Gantt chart. If we take another example of Johnson's rule and try to draw the Gantt chart for more than one workstation, we can take this particular example. In workstation 1, here number of jobs has been increased from 5 to 10 from the previous sum to this sum. Under workstation 1, A, B, C, D, E, F, G, H, I and J has the processing time simultaneously at 3, 4, 3, 6, 1, 3, 2, 1 and 8, 4. And under workstation 2, A to J job has the processing time of 1, 4, 2, 1, 2, 6, 4, 1 and 2, 8. So as we have previously mentioned, we need to draw the scheduling. We need to do the scheduling based on Johnson's rule and then draw the Gantt chart. Now, if we try to schedule the two workstation based on the Johnson's rule, let's see here first what are the options that we are having. The shortest processing time on workstation 1, if you see carefully, job E and job H are a tie. Job E, again I am repeating, job E and H under workstation 1, job E and job H are a tie for shortest processing time. So as we have previously mentioned that if two works has been tied at the shortest processing time, so what we will do, we will try to arbitrarily choose any one of it. So I have subsequently chosen E, and then automatically at step 2 I will be choosing H. So step 1 and step 2 is E and H. Now if we move on to step 3 here, we can see here there are 3 jobs. There are 2 jobs that are subsequently having the least amount of time. In case of workstation 2, that is work A and work D. And since H has already been assigned at the second spot or second step, I have eliminated H. So definitely I'll not be taking H into consideration. I'll only be taking work A and work D, which have the shortest processing time under workstation 2. And according to Johnson's rule, what we will do, we will be putting them at the end of the schedule. At the end of the schedule or as late as possible. Since again it is a tie, what we will try to do here, we will try to randomly select any one of it. So I have chosen A for the last position and then placed D just before the last work. So at step 4, if you see here carefully, we have successfully placed the work E, we have successfully placed the work H, we have successfully placed the work A at the last, and D just at the before position of A. So now we have eliminated E, H, D and A. Now if we go on, G is the G has the shortest processing time in workstation 1. So I'll be placing, since it is a work of workstation 1, I'll be placing it at the beginning as early as possible. So after E and H, I'll be placing G in step 5 and have successfully eliminated the work G. And now if we have placed G, the next shortest processing time is at workstation 2 of work C. So according to Johnson's rule, what I will do, I'll try to place it as late as possible. Now one thing I have missed here, if you carefully see that not only C but also I has the shortest processing time in case of after placing G. So again I'll be randomly selected in selecting any one of the work between C and I. So I have selected C and then I'll be putting I. So in step 7 we have successfully put or arranged the work C and I from the back and have successfully eliminated G, I and C. Now if we look at the shortest processing time in workstation 1, we can have the work of F, which is at 3. So that will be placed after G. B now has the next shortest processing time both in workstation 1 and 2. I'll take workstation 1 and place it after B, and the job that is remaining, that is J, which I'll be placing in between the place of B and I. So now at step 10, I have successfully scheduled the entire work based on the Johnson's rule. Now, if we want to find out the make span or the work span for the entire work process, what we can do, we have now the scheduling, that is E, H, G, F, B, J, I, C, D and A. So if we start the first work at workstation 1, E, so the starting time will be 1. So the finishing time will be 1 also. Simultaneously H will start at 1 and finish at 2. G will be starting at 2. It has a processing time of 2, so it will be finishing at 4. F will be starting at 4, processing time of 3, ends it at 7. Simultaneously we can have the following works at B of starting at 7 and ending at 11. J has the starting of 11 and has an ending of 15. I has a starting of 15, has an ending of 23. Simultaneously A, the last work, will have the starting time of 32, processing time of 3, ends it at 35. So initially we will be putting, as we have mentioned, the idle time at the end for workstation 1. So simultaneously I'll just not put the values here. What I will do initially, I'll just mark the kind of flow that is there or the scheduling that is there under Gantt chart for workstation 1. I'll draw E to H, H to G, G to F, F to B, B to J, J to I, I to C, C to D, D to A, and then A to idle time. But I'll not mark anything right now. Now if we go back to workstation 2, the work of workstation 1 of E has finished at 1. So definitely it will be starting at 1, having a processing time of 2, it will be finishing at 3. H will be starting at 3, processing time of 1, finishing at 4. So if you now carefully look at it, up to, if you can see, work C, up to work C, there is no idle time provided within that period of time. There is no idle time provided for workstation 2. But if you see now, D in workstation 1 has ended at 32, but the work C at workstation 2 has ended at 30. So the work D at workstation 2 cannot start before 32. So there will be another idle time there. So if I put that and then simultaneously again end it at 33, A at workstation 1 has finished at 35. So the A work cannot start at workstation 2 at before 35, but D at workstation 2 has ended at 33. So again 2, there will be idle time. So if we continuously complete that, and we can have now the work span at 36. So before going on to the scheduling of workstation 2, I'll complete the Gantt chart of workstation 1. I'll just put in the values, and at the end, that A to idle time, the space that I have kept, I'll write idle time at 1. Right, because the work span is 36, but the entire process of workstation 1 is completing at 35. So I'll write idle time 1. Now if we start off the Gantt chart for workstation 2, I'll start off with idle time because E will start off at 1. So idle time at 1 to E, from E to H, from H to G, from G to F, F to B, B to J, J to I to C. That will have the simultaneous kind of processing time. that will have the simultaneous kind of processing time. I'll just put in the values respective of the processing time of the works. So 2, 1, 4, 6, 4, 8, 2 and 2 has been put. Now as I said, C is finishing at workstation 1 at 26, but it cannot start off the work before 28. So from here I'll have after C one idle time. I'll have two idle time rather, because the work is ending, the previous work of C is ending at 30 and D is starting at 32. So idle time 2, idle time 2 to D, processing time of 1. Again from D to A I have to wait because the work is still being continued at workstation 1. So A is ending at workstation 1 at 35, but D at workstation 2 is ending at 33. So again there will be an idle time of 2 and then the completion of the work A. Hopefully these two examples have absolutely cleared out the Johnson's rule and how to draw the Gantt chart related to simultaneous workstations.